Generating text with an LLM is a relatively solved problem. Executing that AI-generated output securely as code in a live enterprise environment is a completely different engineering challenge. If an AI hallucinates a vulnerability in a block of PHP or JavaScript, and that code is deployed directly into a learning management system, the entire database is exposed to immediate compromise. To bridge the gap between AI generation and secure execution, LearnAdapt developed the PedOS plugin pipeline. The workflow begins at a basic interface, where an educator or non-coder submits a plain English prompt describing the tool they want to build. The end state is a fully functional rendered UI plugin that sits inside a learner's dashboard and actively writes telemetry data to a learning record store. This creates a central routing problem. How do we take an untrusted text prompt and convert it into a live telemetry state without polluting the core database? The solution relies on three defensive structures operating in sequence: an iterative agent swarm, strict static application security testing, and a tiered telemetry sandbox. By physically separating the generation of the code from the permissions required to deploy it, this architecture allows anyone to build educational software while strictly controlling operational risk. When a user submits a plain English prompt, it enters the system through the Agentic Studio and is logged as a raw input. The intake mechanism structures this request by creating a specific agent-tasks record, assigning it a unique ID for tracking throughout the build lifecycle. This animated flowchart shows the path of that task through a multi-agent worker swarm. A data packet moves sequentially through 5 specialized nodes: a planner, a researcher, a coder, an analyst, and finally, a coordinator. Instead of attempting a brittle, single-shot generation, the swarm iterates. The agents collaborate to refine and correct the logic at each node. The resulting output is a conventional, versioned plugin package. It contains standard PHP initialization files, JavaScript, CSS, and any necessary SQL migrations. Generating standard inspectable code packages instead of opaque AI outputs is the first requirement for establishing system security. We have to be able to read exactly what the AI built. At this point in the pipeline, every line of generated code is treated as hostile. Before it can move forward, the package passes to the SecurityManager, which enforces a mandatory static application security testing, or SAST, gate. This diagram illustrates the SAST process. The code packet attempts to clear a firewall barrier, but is rejected and flagged for containing banned PHP functions like exec and eval, along with recognizable cross-site scripting patterns. The SecurityManager also scans for CMS API leakage, checking that no rogue REST routes or WP-JSON endpoints are registered by the plugin. Next, it enforces a strict telemetry bypass prevention rule. Generated plugins are explicitly banned from making direct calls to legacy platform endpoints like /API/xAPI. All telemetry must route through a new, highly restricted endpoint. Once the code scores high enough to pass automated SAST, it enters the second phase of validation, the manual admin review queue. When an administrator clicks Approve, the system does not simply change a database status. The approval action triggers an immediate server-side SAST revalidation run just milliseconds before deployment. This ensures that the exact artifact being deployed is the one that passed inspection, closing a specific vulnerability window known as a time-of-check to time-of-use attack. System automation cannot be trusted on its own. An immutable, double-checked verification layer must stand between the initial generation of the code and its final deployment. Immediately after the artifact clears that final SAST revalidation, the deployment phase begins. A component called the PluginDeployer takes control, moving the approved files into the live plugin registry and assigning them a version number. Deploying on shared hosting environments introduces severe constraints, specifically regarding restrictive directory permissions and issues with symlink traversal. To bypass these file system limits, the architecture uses a strict copy mode to publish the files directly into the current runtime directory. This visual maps the static asset security rule set for that directory. JavaScript and CSS files, highlighted here in green, are explicitly allowed and return standard HTTP 200 responses. Conversely, direct URL requests for any PHP execution are strictly blocked, forcing an HTTP 403 forbidden error. At the application level, a hardened runtime loader wraps the execution, catching and neutralizing any broken active plugins before they can trigger a fatal error and blank the global site. These physical, file-level access restrictions serve as the ultimate failsafe. If a malicious plugin somehow bypasses the logical SAST gates, the server hardware itself prevents the code from executing directly. The final architectural hurdle is allowing users to safely preview a plugin's interface without accidentally injecting test data into the main database. LearnAdapt solves this using a tri-state telemetry sandbox model. This diagram outlines the 3 execution environments. The first state, illuminating here, is the Studio preview. It renders the HTML and JavaScript logic, relying entirely on mock data with 0 database persistence. This allows a non-coder to test the generated user interface immediately after prompting it, using strictly local data. The second state is the directory preview. This environment loads approved plugins inside a sandboxed iframe, but strictly blocks any data writes. This state executes the approved code so the public can evaluate it, but stops all telemetry persistence because the viewer has not explicitly installed the plugin to their profile. The third state is the installed runtime. This is the only environment in the entire pipeline allowed to persist telemetry. To reach this state, 3 conditions must be met. The user must have an authenticated session, the plugin must have a globally active registry status, and there must be a personal installation record for that specific user. Only after all 3 conditions are verified by the gatekeeper endpoint are valid payloads finally written to the xAPI events database table. Structurally decoupling visual rendering from data persistence is the only secure way to allow the public preview of community-generated tools on an enterprise platform. We can trace this entire architectural journey through a verified production case, Task 27, known as the PedOS reflection check. This system log readout displays the success markers for that specific artifact. It passed the SAST gate with a score of 95 out of 100 and successfully generated telemetry event 131. Production testing confirmed that the browser preview remained fully interactive during evaluation, while successfully insulating the core platform data from uninstalled interactions. Despite these structural controls, the system still faces ongoing operational realities. The most persistent risk is the inherent non-determinism of large language model providers, combined with unexpected API quota limits during the generation phase. To mitigate this, a scheduled automated canary worker continually executes small generation tasks, monitoring the provider's stability and triggering alerts if the swarm fails to connect. This pipeline proves that developer-level strictness, strict code versioning, and zero-trust security gating can be fully automated behind a simple interface. By solving the execution risk, the platform safely democratizes the creation of educational technology.